Okay, so I'm still following the book, and before talking about, before introducing the concept of thermodynamic potentials, which will be generalizations of internal energy and entropy to other situations in which the system is suffers transformations of different kinds. Let's talk a little bit more about ideal gases and phase transformations. Okay, so today I want to talk about the Clapeyron equation for transformations between liquid and gas. Yes, you have a question?
Not a question, but I tried to calculate lambda, the length for a nitrogen gas.
Mm-hmm.
And then I got like 0.04 nanometer at room temperature.
Mm-hmm.
So,
Is that small or big?
yeah, that's small.
Okay. That's what it should be, more or less. Okay, the order of nanometer. Okay, so let's consider a non-ideal gas, so a real gas, and let's look at isotherm of a real gas. Okay, so let me first draw the drawing and then we'll discuss it. These are supposed to be lines of constant pressure, so okay, so the idea is the following. We have our favorite piston, and inside there is some gas. And we assume the temperature of the gas is constant, so it can exchange heat with the environment such that the temperature is constant. And so if we follow what happens to our gas when we decrease the volume, so we push the piston down, we see that we can compress and compress the gas. So if the volume is very, very large compared to the number of particles that we have, so if the density of the gas is small, then the gas behaves like an ideal gas. Okay? Then we start compressing the gas, and it starts behaving in a different way from an ideal gas. And at a constant temperature, if the temperature is sufficiently low, what happens is that when you reach a critical pressure, some liquid starts forming, so you keep pushing this down. Some liquid starts forming, and the pressure remains constant at constant temperature. So these are isotherms. So here we have gas or vapor, gas, liquid plus gas, liquid. we keep compressing the gas until all gas goes. So let's assume we are following this isotherm here. Okay, we move around along this line, and then at a certain point we start. Part of the gas condenses. The liquid and gas are in equilibrium with each other. The pressure remains constant until all gas is turned into liquid. And then, you see, I made it on purpose. I mean, these lines, the derivative of these lines are much bigger than the derivatives over here. Because compressing a liquid, liquids have very small compressibility. So if you now try to compress a liquid, change the volume, even by a little bit, the pressure goes up quite fast. Okay, so this phase here is called, it's a phase of coexistence. Okay, in this region here, you have both liquid and gas, and they are in equilibrium. From a microscopic point of view, this does not mean that half of the particles, or like a third of the particles, are liquid and 2/3 are gas. This is all. This is true, but it's not the same particles. Okay, particles get exchanged. They go out from the liquid. They go in the gas phase. Particles from the gas come back, and so there is a continuous exchange. But the quantity of liquid and the quantity of gas, the mass of liquid and the mass of gas, if you want, this is a macroscopic observable, so changes very little over time at any given point here. All right, so we want to use thermodynamics to understand this region here, and in particular, to understand what happens when we change the temperature. So what is dP and dt at constant volume? Because the volume is constant here, so we can think about it. Okay, so is this diagram familiar to you? Have you seen it before? Yes, no, maybe? Okay. So some of you have seen it, some of you have not seen it before. So there is a critical temperature here which corresponds to a critical isotherm. And for temperature above this, there is no liquid-gas transition. Okay? The concept of liquid and gas, I mean, the phase to the left and to the right of this point and above this line are not so different. Okay? It's always gas. You have to go to sufficiently low temperature, and then there is a critical volume, which also gives a critical pressure, below which we have liquid, and above which we have gas. Yes? What? Oh, do you want me to repeat what I just said? Okay, so these isotherms correspond to different temperatures. Temperature increases in this direction. Okay? So this isotherm here corresponds to a temperature Tc. And if you are at temperatures above Tc, no matter how much you compress your system, you're not going to get any liquid. Okay? Below this Tc, when you compress, you get liquid, and then liquid and gas, and then you get liquid. So there is no, there is no phase transition above. below below this temperature, there is a phase transition when you compress your system, and the phase transition goes through a phase of phase coexistence. Phase coexistence, to coexist means to exist together. Okay, so there is a phase in which together there exists gas and liquid. Okay, so let's consider the equation. Let me copy it right. du by dv, u being the internal energy, is T dp by dt at constant volume minus P. Do you remember how we got this equation? How did we get it? Just a second.
From the first law.
From the first law. What was your answer? That he just said? I think we got it from the second, from the expression of the entropy, right? We got it from the expression of the entropy, assuming that the entropy is a state function, and therefore ds is an exact differential. And then we use the fact that for exact differential, the second derivative is commutative, so you can take the derivative with respect to the temperature or volume temperature. This does not change. This gave us this equation. Okay. Maybe I should. Okay, let me leave these things on the back one. So let's consider a mole of gas. When we compress it, we will have some mass which is in the gas and some mass which is in the liquid. So we have the total mass of the system, which is conserved, will be the sum of the mass in the gas and the mass in the liquid. We also consider the specific volume of liquid and gas, which is the inverse of the density. And so the total volume of the system can be written as the mass of the liquid times the specific density, the specific volume of the liquid, plus the mass of the gas times the specific volume of the gas. Okay. Also, the internal energy can be found as a sum over the two substances, because we can divide the system in two, and it will be the mass of the liquid times the specific energy of the liquid, which is just the energy of the liquid, the internal energy of the liquid, but per unit mass. Okay. Let's change the volume. Let's change the volume. If the change in volume is positive, what happens? A little bit of liquid goes into gas. Okay? So we lose a little bit of liquid, and we get a little bit of gas. And this depends on the amount of volume that we change. But clearly, I mean, the same mass of liquid is lost that is generated in the gas. I mean, mass is conserved. This equation has to be satisfied. So we can just drop the M and G indices on the differential. So the finite terms do sum to V. And we get this equation. So dV is E gas minus V liquid times dm. And doing the same reasoning on U, when a little bit of mass from the liquid goes into the gas, we get a change in internal energy, which is just UG minus UL times dm. But we know that then when we want to transform a little bit of liquid into gas, we have to give it some heat, right? There is a specific heat of vaporization, which is a constant. Depends on the material, clearly. I mean, it depends whether it is water or I don't know, anything, nitrogen, whatever. When you want to transform a little bit of liquid into gas, you have to give it some. This thing is a function of the temperature, clearly. That's not a big, great end of the pressure, of course, but it does not vary too much on the in the range that we consider. Okay, so now we have to find dq, right? But dq is not difficult to find. Which equations should I use? What do you think? dq. So what do we have here? We have du, we have dv. So which equations should I use? The first law, right? So dq is equal to du plus p dv. Okay? So dq over dm is equal to du over dm plus p dv over dm. And therefore, this thing is ug minus ul plus p vg minus vl. And we say that this is equal to lambda. Okay. Now, what we wanted to use this equation. We can get du by dv by taking the ratio of these two differentials. So we have the following. Maybe I can do it over here. And from this equation, I can write this as lambda divided by Vg minus Vl minus P. And if I insert this in the left-hand side of this equation, I get that the result that I wanted, dP in dt, is equal to lambda divided by T okay. This is called Clapeyron equation. And it tells you how, for a real substance, the saturation pressure changes with the temperature. And it connects this quantity, the pressure, the derivative of pressure with respect to the temperature, to the specific heat of vaporization, on which it clearly has to depend, because we're looking at vaporization, and the specific volumes of the gas and liquid phase. So let's make a little approximation here. So this is the specific volume of gas, and this is the specific volume of liquid. Which one is bigger at given pressure, given temperature? This is fixed pressure, fixed temperature. Which one is bigger? What is? The one for the liquid. This is the specific volume. So it's the volume for unit mass. So if I have 1 gram of water in liquid form, it occupies how much? 1 cubic centimeter, right? That was the original definition of gram. 1 cubic centimeter. 1 gram of steam, it takes a much larger volume, right? These are the inverse of the densities. The density of the gas is much smaller than the density of the liquid. So in practice, I can neglect this second term here. And for a gas at a given temperature, at given temperature and at given pressure, how can I get this? How can I get this density here? Let's make the approximation is an ideal gas, which is not, otherwise you would not condense it, but let's make this approximation. If we make this approximation, we can use that PV is equal to RT and KBT. But I'm talking about 1 mole, so I can use R. Beware, you have to be careful when you do exercises and work out numbers that, you know, if you're talking about moles, you have to use R. If you're talking about number of particles, you have to use NKB. Okay, it's important. So, so PV is equal to RT, but we say that Vg is the volume divided by the mass, the volume of 1 mole divided by the mass, the molar mass. And so okay? I've just used this equation into here. So let's look at this equation. This equation says that dP by dt is equal to lambda m over r t square 1 over p. No, sorry, p. No, 1 over p. Because, sorry, my mistake. This was in denominator here. Times p. How can I solve this differential equation for p as a function of t? We separate the variable. So we write dp over p is equal to lambda m over r t squared. So this is the differential of the logarithm. And this is lambda m over r, the differential of minus 1 over t. So if you solve this equation, you find that p is equal to a constant times e to the minus lambda m over r divided by t. Does this look familiar? This is the same functional form that we found last time when we did the vaporization of the solid. There the calculation was much more complex because we had to consider the entropy of the solid, the entropy of gas. Here it's only, and then we had to use, you know, the Sackur-Tetrode constant, which contains h bar and so on and so forth. Here we only use thermodynamics and, you know, just a very rough approximation, but works quite well for the specific volume of a gas. And we find the same functional form. Of course, we cannot find the constant in front, because the constant in front, as I showed you, contains information about the microscopic structure of the liquid. In that case, it was of the solid. In terms of the Debye's temperature, it contained H, Planck's constant, and so it contained a lot of information more. So from this equation, we only find the pressure as a function of the temperature, apart from an overall constant that one could get from the experiment, actually. One runs the experiment at different temperatures, does a fit of the pressure with this form, and then you get the constant. If you don't know what lambda is, you can also get it from here. But usually lambda is not difficult to measure. Okay. So for example, water at boiling temperature, lambda is something around alpha kilocal per gram. Okay. So first of all, you have to bring water. So this is what happens when you want to cook spaghetti, right? You put water in the pot, then you turn on the fire. Then the first thing that happens is that the temperature goes to the boiling point. But that's not, once you get to the boiling point, you still need to put in heat in order to make the water evaporate. Okay? So the first thing that happens is that your system goes to the boiling point, which is a function of the pressure, and that, you know, if we consider 1 atmosphere, it's 100 degrees Celsius. So water goes to 100 degrees Celsius, and then you have to put in calories to let it evaporate. Okay, and these calories, this amount of heat that you have to put by keeping the fire on under the boiling pot is around 540, I think, calories per gram for water. Other substances have different. Okay. So, look at this equation for a second. I also want to talk a little bit about water, because the book says something which is quite interesting. And suppose we are doing, okay, first of all, let me stop for a second. Is this clear? You have a question? No, you're just, okay. So, is this clear to this point? I mean, it's the fundamental equation is this one, which we deduced from the second principle of thermodynamics. And then we then looked at what really happens when I change the volume. You have to look at the change in the internal energy. And this is a bunch of constants that depend on the system. And then we deduced an equation for, we used this definition of dq by dm as a function, which is lambda, that we can measure in a lab, and then we can put it in our equation to see if we can do non-trivial predictions. We used the first law explicitly, and then we get this equation here. Then if we do a little approximation, which we neglect, we say that the density of the liquid is much, much larger. In fact, the density of water at these boiling points is more or less 1,000 times the density of steam. So it's a good approximation, very good approximation. If we do this approximation, then we do the further approximation of taking an ideal gas. Then we get an equation which is very similar to the one that we got yesterday when we were considering vaporization. All right. Yesterday we got more information because we even got the constant right in front, which was a hat trick. Okay, now suppose we are doing the same. Suppose we do the same process, but instead of looking at liquid and gas, we look at solid and liquid. Okay. Apart from this thing that we used afterwards, before here, I mean, there's nothing that tells me that I'm considering a liquid and a gas. I mean, also solid, and also solid has an internal energy per unit mass, has internal volume per unit mass. And so I can go through the same equation and end up with dp by dt, which is lambda, which now will be not the specific heat of vaporization, but the specific heat of melting. V liquid minus V solid. Okay. So usually the density of the solid is high. Yes. So the question is whether you can take you can do perform this transformation at constant volume in a solid. The question is yes, only that the pressure that you have to apply, they are much, much bigger than the ones we are considering now. Okay, you can compress a solid. It's not that the compressibility of a solid is infinite. You can compress. Solids are usually elastic, or so you can actually compress solids, but you have to apply pressures which are thousands of atmospheres. But you can do that. So there is nothing in principle wrong with this thing applied to a solid. It's just the numbers that enter into the games are much, much bigger. You can maintain, so you can do this transformation at constant volume, for example. You do it in the kitchen every time, right? You have you ever seen this? You have this, what are they called? Pressure pots. Yes, these are fixed, right? And the volume there is fixed. So you do this, and it's fixed up to a certain point, because then there is a valve that comes up and the steam goes out. So you want to maintain a certain pressure constant. But up to that point, the volume is gone. You can think of doing the same thing in melting a solid into a liquid, but you have to apply much, much bigger pressures, okay, to maintain the volume constant, and taking derivatives at constant volume. So there is nothing wrong with it. It's just that it becomes less intuitive because we are not used at those forces in everyday life. So the volume of the liquid, the specific volume of the liquid is usually larger than the specific volume of the solid, right? When you have a solid, this is more compressed than the liquid. It has higher density. So this thing is usually positive. In fact, you see here what happens. If you increase the temperature, the pressure increases. But there is one very important counterexample. Not to this formula. The formula is always valid. But to this fact that I said that solid are more dense than liquid. I don't know about that. But what? Ice. Why does ice float in water? Because it's less dense. Right? So for ice, for water that goes into ice, this thing has the opposite sign. So dP by dt is negative. Okay? This is very peculiar because of the structure, the hydrogen bonds in water. So you can explain it at a microscopic level, but in the experimental evidence is just put a piece of ice in your water. If it floats, it means that it's lower density. Archimedes principle. Okay? So, but this is a very, very important, geological consequences. Because if dP and dt is negative, it means that if I increase the pressure, the critical temperature for freezing goes down. Okay? So it means that if I have, let's say, at 1 atmosphere, water solidifies at 0 Celsius, freezes at 0 Celsius. Okay? But if I apply a pressure, the freezing temperature goes down, goes to -5, -6, -7, -8, -10. Okay? So it means that if I am at 0 Celsius and I apply pressure, water melts. Okay? And this is what happens with glaciers. So have you ever seen glaciers on the mountains? They can go around the rocks. How do they do that? Because where is it? Okay. So let's assume there is a piece of rock here. So we see it from outside, and there is a piece of ice here. Okay. So ice wants to flow in this direction, but there is the rock that stops it. And ice weighs a lot. Okay, these are things which weigh millions of tons. Okay? And it presses on the rock. So the part of ice which touches the rock, it's at a huge pressure. Its freezing temperature is not 0, like ice which is up here. It's minus 20. Okay? So if the ice was at minus 10, the freezing temperature here is minus 20, which means that you can get water in liquid form at minus 10. So there is water here, and this slips around. And as soon as the pressure returns to 1 atmosphere, as soon as the pressure returns to 1 atmosphere, then the system freezes again. So you have glaciers that can go around rocks because they melt when they touch the rock because of the pressure, because of this phenomenon, and then freeze again when they come out. Okay? So as you see, this is also valid for solids, but you have to use a huge pressure to do this thing. You can also, you can generate very large pressure in your kitchen. If you take a knife, okay, take ice, take a knife, okay, and then like this, and then you push it down. The force that you apply is a few newtons. If you're strong, you can apply, I don't know, 30 newtons. But the surface on which it's applied, it's extremely small. So the pressure is going to be huge. And in fact, if you do this experiment, you can actually ice melts around the tip of a knife. Okay, if you have ice cream, which is which is frozen a lot, it's very cold. If you go with the spoon inside, you press a lot, you see that it melts around. Okay. Ice cream is a strange substance because it contains air inside, so it's a sort of foam. But the concept is the same. So you can have melting of water here, because even if the knife is at minus 10 degrees, doesn't matter. You can do the experiments, put the knife in the refrigerator and do the experiment with but don't touch the knife with your hands. Use some gloves, because otherwise you get stuck to the knife. Okay? As soon, of course, I mean, you have to be careful, because as soon as the water moves out, it will freeze again. So, but anyway, I mean, there is experimental evidence in the glaciers. So glaciers move, and because of this phenomenon. All right. Okay. You have any questions? No? I thought the cameraman had a question, but you were just adjusting the camera. All right, so let's look at a concrete example of a model that has this behavior. Okay, and it's the van der Waals gas. So the equation of state for the van der Waals gas, and again, I'm considering just 1 mole of the gas. So this is the volume of a mole, and this is the constant R. as in the case of ideal gases, there are no gases which are perfectly van der Waals gases, okay? But van der Waals gases are a very good approximation to many, many substances. In principle, all of them, but the approximation for some of them is better, for others is good. So depending where you put your cutoff, you can talk about so many substances. Okay? A and B are coefficients which are dependent on the gas, on the substance. Okay, so for water, there will be something. For nitrogen, there will be something else. For helium, there will be something else, and so on and so on. Okay. So if you plot the isotherms of van der Waals gases, they look like this. So first of all, at very large volume, you can neglect this term, and you can neglect this, right? Because this goes to 0, and this, with respect to V, goes to 0. So you recover the ideal gas. Yes?
What main property characterizes the van der Waals gases?
Okay, what are the main properties that characterize van der Waals gases? So the question should be read in the other direction. Which real gases behave like van der Waals gases? And the answer is almost all of them within a certain approximation. So we expect a lot from this equation. We expect that it actually has a behavior like this, that we observe in a laboratory. Okay? So for the remaining 35 minutes of the lecture, what I want to show you is that this is actually true, that the phenomenology of the van der Waals equation is the same as the phenomenology that we observe in a lab for a gas. The precise numbers that you get are off by 10%, 20%, depending on the gas. But the phenomenology is correct. Okay, so as an exercise for you, you can use some software to plot this equation for a constant t. And you can do this online. There are open source softwares that can do this in Linux or any operating system you want. Okay? What you will see is that for very large temperatures, this looks a lot like an ideal gas. Then you lower the temperature, and you start seeing something like this. But not quite. There is just one curve at which, for a critical temperature, at which you have a flex. And then they start doing like this. Okay? So it seems like there is a point here in which the first and second derivative vanish. There is only one temperature at which this occurs. But then when you go below, clearly, I mean, this is a polynomial equation. You cannot have curves, isotherm curves, which look like flat. If all the derivatives of a function are 0 in an interval, then the function is a constant. So this could never have been. But just check for yourself what you get. And so they have two bumps, and then they go down as an ideal gas for very large volume. So let's look at one of these isotopes. So the behavior is correct up here, but down here, maybe it's correct, maybe it's not, but needs to be interpreted. Yes?
Would I be wrong if I look at, for example, that maxima there, and I compare it to those isobars?
So the question is, if I look at this maximum here,
As the flattens in the upper diagram. Yes.
as the beginning of the flat,
The whole
No, you will be wrong. It's not this. This curve, you can actually get this part here. I can, let me talk about this just now, okay? So let's take one of these isotherms. I exaggerated, it's never like this, but I exaggerated the situation. So when you decrease the volume, this goes to zero asymptotic. When you decrease the volume on this isotherm, your gas follows this thing up to a certain point, and then it starts liquefying before you get to the maximum. Once it starts liquefying, the pressure is constant until it gets to this region and then goes up. Then you have liquid. Everything is liquid here. 100% of the substance is liquid. If you're very careful, you know, if you are very careful and you prepare your gas in a very clean container with very smooth boundaries and so on and so forth, then you can keep 100% of your substance as a gas up when you reach here, and then the system collapses and goes back to this line. This is called supersaturated regime. It's vapor with a U. No, without U. So the flat line is not the maximum. It's really something different. Okay? But if you're not careful, you know, if you're doing an experiment without really looking for this thing, you will never find it. What happens is that you get at a certain point and then it starts liquefying until it's all liquid and then it then behaves. Okay? So we want to understand where do we have to put this line? Where do we have to put this line? I mean, do we have to put it here? Do we have to put it here? Do we have to put it here? Like this? Hmm? Hmm? Okay, so our friend says that we should put it such that the areas above and below are equal. Why? It's the law. Hmm? And then? Because it's prettier like that. We don't need to introduce another law of thermodynamics, okay? 3 laws are enough. We can actually find, the answer is correct. And I will show you why it's correct. This is called Maxwell's construction, by the way. The area under this curve has to be equal to the area under this curve. Let me remind you that this is an isotherm. So T is a constant along this line. Let me first of all prove something to you, that the work done by a reversible isothermal transformation is 0. Isothermal, cycle, not just transformation, of course, it has to be a cycle. So if we have a reversible isothermal cycle, then dW is equal to 0. Can any of you see how to prove this statement? Can you see it? What would you do? The total contour of the total area of what will be 0? The change in the energy will be 0 because it's a cycle, right? And then is this enough to prove that the work is 0? We have seen many cycles in which work is not 0. I don't want to specify the cycle. I just want this to work for any cycle. So, okay, so du is 0 because u is state function. Which other state function do you know? Entropy. And so ds will be, this is a reversible, okay? So the entropy will be 0. And for reversible, the entropy is equal to dq is the integral of dq over t. But if t is also isotherm, then t is constant, and then this becomes dq over dt. So du is 0, dq is 0, so dw, which is equal to dq minus du, is equal to 0. Okay? Now let's take this thing here and let's build an isothermal cycle. So the isothermal cycle that I want to build is the following. I go down here, up here, back here, and back to the beginning. The work has to be 0. But the work is the area enclosed by the cycle, right? So I have to, first of all, I have to, this is an integral in which, you know, the integral of p in dv will be this, actually this minus this, because this is encircled in a clockwise direction, this is encircled in an anti-clockwise direction. So it will be area 1 minus area 2. This has to be equal to 0. So the two areas are equal. Another way, if you don't like this way of looking at the thing, you can calculate the area which is under the first part, which is this, and then subtract the second part, which is this. This then comes with a positive sign, this comes with a negative sign. You get the same result. You might, at this point, have a question, actually an objection to this thing here. And it's the following. So what we build this cycle. This is an isothermal cycle, right? But the area under it is not 0. What's wrong with it? what are the requests of the theorem? That it's isothermal and reversible. So if it is isothermal and the theorem does not work, it means that it's not reversible. Why is it not reversible? Because once you get here, you go from here down and up here, okay? You're assuming that all of your system is in gas, because we are following this line here. And then we have to go on the straight line. But the straight line, there is a part which is gas and a part which is liquid. So I have to, tick my container, and the system goes from liquid to gas, from gas to liquid. Part of the system goes from gas to liquid, and then I can keep compressing it. And this transformation, sudden transformation, which is out of this plane, if you want, because it occurs at pressure and volume and temperature which are constant, but in which a part of the gas just collapses and goes down to liquid, this is irreversible. So these branches might be reversible, but the point that connects them is a transformation which is irreversible. This big cycle does not have this problem, because in the big cycle, this transformation, when you go back here, you have 100% of gas, so the connection is smooth. And when you go back here, you have 100% of liquid, so the connection is smooth. Okay? All right. So this is the proof of Maxwell's construction, that I don't have to, I have to put a point, I have to put a line where the areas under the curve are equal. And this gives me, sorry. This gives me the coexistence curve. Maxwell was one of the greatest physicists of the 18th century. He did everything. He did electromagnetism, Maxwell's equation. He did the foundations of statistical mechanics by taking seriously the work of the engineers that had invented thermodynamics. And James Clerk Maxwell. Okay. Do you have any questions? This construction is not based at all on this equation of state. It's completely independent of the equation of state. Whatever equation of state you have, if it has a non-monotonic region, you have to cut it with Maxwell construction. Okay.
If those two regions are not symmetric, then it will not be like a line, right?
There is always a line that gives equal.
Yeah, here, those areas.
They are not symmetric, by the way.
But it looks,
Well, because I drew it like that. But, so if I do something like this, there is always a line I can put such that the area under this thing is equal to the area under this thing.
yeah, we do a line with some slope.
No, it will be a flat line, constant pressure. I mean, the slope is because I was drawing it like that. But it's a theorem, right? You can always find. can always solve the equation in which the two areas are equal. Even if this is very asymmetric. The higher this goes, the more you have to move the line. Okay, so now let's take seriously van der Waals gas and let's compute some state functions. Okay. So we can solve this equation as P is equal to RT divided by E minus B minus A divided by V squared. If I rewrite this equation in this form, you see what's the intuition behind it. The intuition is that particles are not really point-like. Molecules are not really point-like, but they have a dimension. And the volume, so the volume that counts in my box is not the total volume, but it's the volume minus the total, the sum of the sizes of the particles. Because so if I sum the small volumes of my particle, then I get B. This is the idea. So there is a hardcore repulsion, and the particles cannot be put closer than that. And in fact, if you plot the pressure as a function of the volume, you see there is a pole here. And the pressure diverges at this point. You cannot compress the gas. But this point actually usually corresponds to a density which is so large that the equation is not valid anymore at those densities. So you don't really have an infinite volume, an infinite pressure problem. You have problems much earlier. And the second contribution it has a minus sign. So does it increase or reduce the pressure? It reduces the pressure. So if it has something to do with interaction between the molecules, do you think it is a repulsive interaction or an attractive interaction? Should we make a poll? Who thinks attractive? Who thinks repulsive? No. Actually, anyone wants to answer? Apart from him, we know his answer, right? Repulsive. Why? What is the pressure generated by? The pressure is generated by particles which hit on the wall, right? So in order to reduce the pressure, the particle needs to attract or to repel each other. To attract. So behind van der Waals equation, there is the idea that particles repel at short, if this is the potential between two particles as distance r, there is the idea that particles repel each other at small distances and attract each other at large distances, which is called van der Waals interaction. Okay, and this is correct. Indeed, this is correct. Particles actually attract each other. Typically, the neutral particles attract each other at large distances because they have dipoles. Because they can induce dipole interaction. They can induce virtual dipoles, and and then the dipolar interaction is attractive. It's always attractive. Okay. So there is some microscopic physics that is reflected in this thing here. So this would be the volume, the small volume VI, and this will be the attraction that generates A. Okay. Let's get our favorite equation. And let's look at this equation when P has this form. T of RT divided by V minus B minus A over V square minus RT over V minus B minus A over V squared. Okay? If you do this calculation, this first term drops out with this, and only this thing survives. So U is a function of T, arbitrary. We cannot deduce it from here, minus A over B. So the function f of t is completely arbitrary at this point. We don't have any means of deducing it from van der Waals equation. This was the same situation as for the perfect gas, right? The ideal gas. In the ideal gas, the only thing we could say is that the internal energy did not depend on the volume. It only depended on the temperature. But we could not say how it depended on the temperature. This is because, in some sense, this is a kinematic property, and this is a dynamic property of the gas. This is kinematic because you can get the equation of state, which involves the pressure, the volume, and the temperature. Most of the times, not all the times, clearly it contains a lot of information. But for example, for the ideal gas, the only thing that you need to know is how the particles bounce off the walls. And if the bouncing off the walls is elastic, this does not tell you anything about the particle. I mean, essentially all point-like particles bounce elastically, whether they are relativistic, non-relativistic, classical particles, quantum particles. They have spin, they don't have spin, they have charge, they don't have charge, anything. Okay. So this modification of the equation of state has the same failure, and in some sense, it's also it is also why it works so well. It works so well because it only captures some quantities which are universal for all gases. But clearly there is more to it in real gases than these things here. But we can, and so we get something. We get the volume term here, which is already a good thing. And with the correct sign, because the more you reduce the volume, the more negative is the interaction energy between the particles, and so the internal energy becomes more negative. But about the dependence on the temperature does not say anything. By the way, if here we had something which was non-linear in the temperature, okay, or if we change this exponent, then this trick does not work anymore. And you have a function of the temperature. Because, what I'm just saying that if you, instead of having RT here, you had RT squared, there will not be an exact cancellation between T d by dt of this term and this term here. Okay, so now, in order to go further, let's make the assumption that f of t is just linear, and it's Cv times t, where Cv is the specific heat at constant volume. And plus, then there is an irrelevant there is a constant which we cannot determine and will not enter our calculation anymore. So this is one specific van der Waals gas, not the only one. And I want to calculate the entropy. So in order to calculate the entropy, what should I do? What should I do? When I want to calculate the entropy, I have to calculate dq. Always, when you want to calculate the entropy, in these situations, you have to use dq. So, and dq, we get it from dq is equal du plus pdv, because it's a gas. This is always true. It does not depend on the fact that pressure satisfies this equation or not. I mean, it's always pdv for a gas. So this becomes Cv dt plus A over V squared dV plus RT over V minus B minus A over V squared dV. Okay. Cv dt plus RT V minus B dV. So ds is equal to Cv dt by T plus R divided by V minus B dV. And therefore, by integrating this thing on a general path, about T and V changes, we find that the entropy is Cv log T plus R log of V minus B plus a constant. This constant is dimension full, again, because here we have log of T and log of V. But you see, there is just one difference with the ideal gas case. What is it? V minus B. Instead, for the ideal gas, we have V. So again, we have the interpretation of the volume available. They have to take the logarithm of the volume available for particles to move, which is not V if the particles have a radius, but it's V minus the total volume of the particle, which is B. So an adiabatic transformation for for the ideal gas is ds equals 0. So from this thing here, we find that Cv dt over T plus R dV V minus B is equal to 0. So this means that T to the Cv times V minus B to the R is equal to 0. Is equal to a constant, sorry. Or if you want, by taking the Cv roots of this thing. This is an exponent. So this is, so for an ideal gas, we had what? T to the V to the 2/3, right? Monoatomic and blah, blah, blah. So if this is equal to 2/3, this depends on the specific heat of the gas, which we don't know because it's not defined by thermodynamics up to this point. Then we get the same equation. Instead of having V, we have V minus B. Then let's assume that R divided by Cv is equal to 2/3. For example, as I said, it doesn't have to be, okay? It's just to put some numbers on the blackboard. So we can take this equation and substitute the equation of state. So for an adiabatic transformation, we get T to the, is it right? Yes. T to the 5/3 P plus A over V squared minus 2/3 is equal to a constant. And also this one, if you put A equal to 0, this is the same as the ideal gas. If you now solve for T from the equation of state, you find that P plus A over B squared B minus B to 5/3 is equal to a constant. And also here, if you put A and B equal to 0, put A and B equal to 0, you find the equation of state. You find the adiabatic transformation, the equation of state on an adiabatic transformation. Okay, so we'll stop here, and Tuesday we go to chapter 5. And we'll start talking about thermodynamic potentials. Yes. Yes, all of them have to reduce to ideal gas because the equation of state reduces to the ideal gas one. If you take?
If I take a real gas, it makes a volume large enough. Does it go
Yeah, if you take 1 mole of ideal gas, of a real gas, and you take the volume very large, it means that the density is very small. It means that the interaction between the particles is very small. And so it goes to an ideal gas. Remember, if you are not talking about the moles, you have to put here the number of moles. Okay, and here the same. As I said, when you look at these things, you always have to you always have to sum things which are extensive or intensive. You cannot sum intensive or extensive variable. Right? So B actually scales with the size of the system, with the number of moles. Okay, this is for 1 mole of ideal gas. Okay.